Okay, we just got done looking at the robot lab, and we're going to be watching a very short video today.
I actually need two, and then I also measured in
Who is that?
It's my friend.
Oh, okay.
Could I?
You can just use one. That's
Okay,
fine.
I'll just use
Yeah,
the
that's good.
one I'll put-
What kind of? That was a marker that kind of spotted.
Yeah.
Okay, that's good. It's kind of artistic.
Well, mine, I didn't even realize it went through the, I needed to do it through the center, so there's two triangles on there, so it's kind of confusing.
Okay, as long as you figured out,
Yeah.
you eventually went through the center, right?
Yes.
Is that what this score is? That's all I need.
Okay.
All right. I want to, if I can have your attention now, we're going to have a very short video, and then we're going to wrap up the thing about temperature scales. This video, the guy who made this Veritasium videos, he made several ones about measurement. And I have two people, you guys both turned in a little extra credit thing about, it was 2019 that they actually did change several of the SI units. They think they're going to change it for the last time, they believe. And so Legrand K is, and if we have time tomorrow, I'll show you a little video on that too, but I looked it up, they have a brand new video on that, getting rid of the. So Legrand K is still going to be there, and they'll take measurements just to see what does happen over time to those pieces of metal. But they replace that. So, but this one has to do with temperature scales. And when I first saw this, I actually learned quite a bit. I did things I didn't know about temperature scales. So I'm gonna have you watch this. And if you could hit the first light switch for me, please. It's about 8 minutes long. Not a huge video, but. Everybody ready?
He took the
Ready?
temperature water freezes at and said that's 0. And then he took the temperature it boils at and says that's 100. And he figured 100 was a good amount of demarcations to make in between the two.
Right?
Yeah.
Except that's not what he did.
Really?
Celsius never devised nor used the scale that now bears his name.
Are you kidding me?
No, Michael, I'm not. This is the Swedish town of Uppsala, located
Uppsala.
70 kilometers
In
north
history,
of
you'll
Stockholm.
look that up. A lot of things
So
happen
this
in
is the house
Uppsala.
where Celsius lived. In 1741, he was professor of astronomy at Uppsala University. And this is the first ever Celsius thermometer. Or is it?
This is the first scale of Anders Celsius added onto an old Lille thermometer. So we have the Lille's scale on the left-hand side, and Celsius's new scale on the right.
These few markings show that Celsius came up with the idea of separating the freezing and boiling points of water by 100 degrees. He made his first observations with the scale on Christmas Day, 1741. But have you noticed something strange about this scale? I mean, 50 is marked in the middle, but the numbers increase down towards the bulb of the thermometer. So Celsius had his scale upside down. He set 0 degrees at the boiling point of water and 100 at the freezing point. Why would he do this? Well, for one thing, Celsius was just following the convention of the other scale on the thermometer. The Lille scale also had 0 degrees for the boiling point of water, increasing down to 150 for his freezing point. And the likely reason both of them used upside-down scales is because they avoid negative numbers. In Sweden, it gets much colder than freezing, but never warmer than boiling water. So you don't have to worry about pesky minus signs, and this helps avoid logbook errors. I think it would be really weird if you had water boiling at 0 degrees and freezing at 100. Wouldn't that be strange? Although it might seem strange today, there is no objectively good reason for preferring an ascending scale over a descending one for measuring degrees of something, like hot or cold. In fact, when Celsius died of tuberculosis in 1744, he was still using this inverted scale. So who reversed it? Who do we have to thank for the modern Celsius temperature scale? Well, in 1745, just a year after Celsius's death, a new column appears in the Uppsala temperature record, using the modern scale, and at the top it's got the heading Ekström. Now, Ekström was the instrument maker at Uppsala. In 1747, another column is added with the heading Strömer. who was Celsius's successor as professor of astronomy. Again, it's got the same modern scale. But it's another professor at Uppsala who claims that he reversed the scale. That's the famous biologist Carl Linnaeus. He says he reversed the scale when he ordered a thermometer from Ekstrom for his greenhouse. Whoever it was, we know that by 1745 there was an operational thermometer at Uppsala University with a scale that we now all know as the Celsius temperature scale. Except, this was not the first such thermometer ever created. In 1743, the year before Celsius died, a French scientist working independently in Lyon created a thermometer with 0 degrees at the freezing point of water and 100 at the boiling point. His name was Jean-Pierre Christin. So why isn't it called a degree Christin instead of a degree Celsius? Well, for a long time, this temperature scale wasn't referred to using either of their names, and instead it was just called the centigrade scale, meaning 100 steps. The problem with this was centigrade has other meanings in French, Spanish, and Italian, where a grade specifically refers to 1/100th of a right angle. So to eliminate this confusion, the International Bureau of Weights and Measures in 1948 decided to rename the centigrade scale after a scientist, bringing it into alignment with other temperature scales like Kelvin and Fahrenheit. They chose Celsius, possibly due to a popular 1800s German chemistry textbook by a guy named Berzelius. In it, Berzelius identified Celsius as the first to devise a temperature scale with 0 at water's freezing point and 100 at its boiling point, propagating the myth that Celsius created this scale. So, is Celsius undeserving of having his name immortalized on weather maps around the world? Well, no. I mean, making 2 marks and deciding on a number of degrees in between them, that is the easy part, which others could, and as history shows, did do. But what Celsius did was he established which physical processes could reliably produce a fixed temperature. At the time when he was working, there were some 30 different temperature scales in use. Some thermometers had 18 different scales on them, some more reliable than others. For fixed reference points, one scale used the deepest cellar of the Paris Observatory. Others used the melting temperature of butter, the internal temperatures of certain animals, or the hottest day in summer in Italy, Syria, or Senegal. These dubious scales, combined with inconsistent thermometer construction, made recording accurate temperatures nearly impossible, not to mention sharing those temperatures with other scientists elsewhere. Celsius solved this problem in a number of ways. He demonstrated that melting snow maintains a fixed temperature regardless of latitude or ambient pressure. He also determined the precise relationship between boiling point of water and the ambient pressure, so that thermometers could be calibrated under any conditions. He made it possible to establish a universal, reliable system of temperature measurement. And this is why Celsius's name is a unit of temperature, even though the scale itself was not created by him. And in fact, today, the Celsius scale is no longer defined by either of water's phase transition points. Instead, it is based off the Kelvin scale, and that scale is defined by setting the triple point of water, where solid, liquid, and gas all exist in equilibrium, at exactly 273.16 Kelvin. This fixes the size of a degree Kelvin, which is exactly the same as the size of a degree Celsius. The 0 point of the Celsius scale is set at 273.15 Kelvin. Now, what all this means is that today, pure water boils at 99.974 degrees Celsius and freezes at negative 0.0001 Celsius. This precision in a nearly universal system of temperature measurement is thanks to a huge number of scientists. So the C after the degree symbol stands not only for Celsius or Christin or Carl Linnaeus, but for the community of scientists whose work over centuries made a scale so robust that we take it for granted.
Okay, he's going to ask you for money. Okay. Did you learn anything there? Something kind of different? All right. Excuse me. Okay. Well, anyway, I have a couple of things, and then we'll move on a little bit. I had these 2 thermometers. I'm going to show it to you. Whenever you, I think I mentioned this before, but whenever you see a thermometer like this, if it's like silvery down there, then that means it's a mercury thermometer. And mercury is a liquid metal, and when you do heat it, the particles start bouncing into each other a little bit more, and then they want to expand. So the metal wants to expand. But where can it expand? Well, they actually made a little tiny hole here, a little tunnel, inside that glass, and that's where it expands. And that's how that works. Now, one thing about this is that this glass down here is incredibly thin. That's why you don't want to go poking around with a thermometer, okay? This is kind of thick glass, but this is very thin. And that's so you don't have to have as much time to let it, the glass get hot or cold, et cetera, et cetera, et cetera. If you see any thermometer that's not silvery, if it's green or red, then it's a colored alcohol, like that. See that? So anyway, mercury thermometer versus that. Last thing I'm going to show you, excuse me. I still haven't. There it is. Wait a minute. Oh, I can't believe it. It may be gone. I don't see it. Oh, there it is. Ooh. It took me, I did this about 5 years ago. It took me about 20 minutes. Oh, wait a minute. No, what's that? It took me about 20 minutes I found a student whose hair, real fine hair. Can everybody see that hair? That took a very, very long time to stick that hair in that little hole. Now that's how incredibly small that little tunnel is. You get that? So that anytime that mercury expands, it's going to go through that little tiny tunnel there. See that? And so that's why it works really well. It expands. Just a little bit of temperature will make that thing go up there. Do you think that's weird? Yes, good.
Oh.
I just want to show you how incredibly small. I don't know how you do that. How do you manufacture something with a hole that's consistent and all the way up there? I don't know how to do that. Yes?
So in the video, he said that originally scale or thermometers were upside down.
Yeah, they actually, boiling water was 0, and then anything else was just a number, not negative, just 5, 10.
So then how did that thermometer work? Because it seems like it would do the opposite.
Well, it doesn't, you would say it doesn't work because you don't like that cold things have a number like 200 and warm things are like 3.
No, I mean like physically.
Oh, it was mercury. Fahrenheit had actually made a mercury thermometer before that, so everything you saw there was a mercury thermometer. Now they had a kind of a glob of mercury and a thin tube, but that tube was probably couldn't even been a 0.5 millimeter. Now somebody had to draw glass into a tube like that, but this is incredibly small compared to that. So the ones I saw in the video, they actually look like a tube that, you could draw a piece of glass out like that. Much bigger than this. So these, just a little bit of increase in temperature or decrease will actually show up on the mercury. So that's a good question. I've never held that in my hand. I've never seen it, but when I looked at it, it had a pretty big glob of mercury and then looked like a glass that went up like that. All right. Put this out of the way. So I think we're about done with that. Let's see, what was I going to ask you about? Okay, any questions on temperature? I want to phase into the last part of the this thing, and if you'll find, there's a page that has this little spider web. I think we looked at it the other day, and where is it? Here it is. Now, this right here, it doesn't have everything, because that would make it hard to see it. But this is how they kind of modernized the metric system and the SI. And like I said, just in 2019, they modernized it again. And anyway, but for right now, they at least, here was their idea. Their idea was that at one time, I remember when I was in college, I think, one of my physics books said something like, we use the MKS system. That was meter, kilogram, second. They said it was based on those 3 things. The original one, meter, liter, kilogram, that's the one I was talking about, the Earth. Remember how you took the Earth, 1/10 millionth of the distance from the North Pole to the equator, got your meter stick, you make your liter, fill it with water. Remember that one? It was those connections. So anyway, when they modernized it, they didn't want to lose that connection. They still have powers of 10, but instead of 3 base units, they have 7. So take a look at these. This is for mass, kilogram, length is meters, time is seconds. When they say amount of substance, they mean in number of particles. Okay, amount of substance, that's in number of particles. That's where Avogadro's number comes in. You got that? Remember the mole? Remember that 6.02 times 10 to the 23rd particles? That's what that is. And then the Kelvin is for temperature, and then the candela is for light intensity, ampere for electric current. Now down here, these are not actually science base units, but they are mathematics. So this is right here at the bottom. Have you guys, this year in math, did you guys use radians, or last year? Did you use radians? Okay. So radians is kind of like a two-dimensional thing, and steradians, or steradians, you know, that's kind of like a three-dimensional angle thing. So they had to use that in some of their definitions like that. Now what I'm going to ask you to do is, I would not ask you to memorize something like that. That's way, I don't need to do that. I do need you to know what the 7 base units are, and then show you that the idea of connecting one unit to another, that's very important. Even in 2019, when they modernized it, that caused a little bit of a ripple effect. Hey, if you're going to change the mole, then that's going to change this over here. Hey, if you change the second, that's going to change that. And so they changed it incredibly small. It's really small changes. But they knew that they wanted to have something to say, we're not going to change it anymore. And that's what they would like to do. And I think that's what they did in 2019. They said, I think we got it now. We don't need to change any definition anymore. Okay, so let's take a look. If you're not a base unit, and there are a lot more things that we measure besides these, where do they come from? Hey, we use meters per second a lot. We use meters per second squared. We use kilogram meters per second squared in here in physics. What's that all about? And you can see that if you're not a base unit, you're what they call derived. You're a derived unit. I have to define you in terms of these. I can use it more than once. I cannot use you at all. But they had to be defined in that. So whoever made this chart in a book, I got this out of a book, he made these arrows, and he said, if I'm in a numerator, I'll go like that. If I'm in a denominator, I'll use a dotted line like that. That's what this means. So if we want to measure area and use SI, we would simply use a meter and a meter square, right? Now we've defined the metric unit. The SI unit is square meter. What about velocity? We use meter and per second. So the SI unit for how fast something's going is the meter per second, and I used 2 base units to define that. Let's go over here. Let's do a harder one. We use newtons a lot. Now the Newton measures force, okay? The Newton measures force. We do a lot of things with force in this class, all right? So the Newton is measuring force, and they defined it as a kilogram meter per second squared. Now, some books would write this. Kilogram meter, this small k, kilogram meter S minus 2. Now, you could write it like that if you don't want to use a slash bar, but does everybody understand that means that's the same as saying kilogram meter per second squared? It's the same thing, isn't it? I'm looking at your half your faces. Everybody got that? Okay. So the question I would ask on the test, I'd say, which SI base units were used to define the Newton? And you go over here and you say, well, meter, that's 1, and second, that's 1, and kilogram, 3. There were 3 base units used to define the Newton. Are you with me? All right, let's try another one. Let's try a hard one. Let's do an ohm. Let's do ohms. First of all, try to figure out which base units were used to define the ohm. Okay? Use your chart. Excuse me. Okay, let's take a look. The ohm, whose symbol is the omega sign, if you know anything about electricity, ohm measures resistance, electrical resistance. Okay, the ohm is defined as a volt per amp. Are either one of those a base unit? You guys, what do you think? Mason, what do you think? Amperes. Okay, that's 1. So keep track of it. It's 1. And then, now I need to find out what a volt is. So I go backwards to the word volt. A volt was defined as a watt per amp. I've already used amp, so go back up to watt. And a watt is a joule per second. So second, that's over here, isn't it? So I've used 2. And then I got to look up a joule. What's a joule? A joule is a Newton meter. It's the amount of force and energy it takes to move a Newton 1 meter in distance. Okay? And so meter is another one. Now I go up to Newton, and I have kilogram meter per second squared. And the one I haven't used yet is kilograms, right there? So, does everybody see that? Now that's the way, they thought that was pretty smart. I do too. So every SI unit that you have is going to be based on these base units here, and they're called derived units. Let's do one more. See if you can figure out what is the unit for measuring power. What is the unit for measuring power?
Watts.
That's what I said. Watt is the unit for measuring power. That's right. Anyway, so you found out what a watt is, and a watt is a joule per second. If you can deliver a joule's worth of energy per second, then that's called a watt of power. Yes?
So, I know the definition for force is mass times acceleration, but what if, like, an object is moving at a constant speed but not accelerating? Does that mean it has 0 force because it has zero
Okay,
acceleration?
wow, you're way ahead of me. First of all, the fact that you knew this is Newton's second law of motion, F equals ma. And if you take a look at it, it actually says that the mass times the acceleration gives you force, right? And that's what you looked at. So you already figured, even though the definition tells you it has to be mass times acceleration. Now, we'll have this whole chapter later, okay? If you know about mathematics, you know that no matter what the mass is, any mathematical equation that looks like this, what if the thing is not accelerating? What if it's going at a constant speed? Or what if it's sitting still? Then the acceleration is what? And if that's 0, 0 times any number equals 0. So that says there is no net force on that object. And we'll have that later because that bothers people. If you push a box along the floor and it goes at a constant speed, if you push it at a constant speed, and I'll say, what's the net force on that box? You say, well, the acceleration is 0, the net force must be 0. But you don't like that because you know you're pushing the box with a force. What you'll find out when we get to that chapter is that you might be pushing a box like this, but something else is pushing it this way. And something else is pushing this way at the same time you're pushing this way, and that's called friction. And when those two balance out, you don't speed up, you don't slow down, you go at a constant speed. That was pretty ingenious that Newton came up with that. And you came up with that on your own. I'm impressed that you thought about that. All right, you ready? All right, are you okay with this? All right, one more time. Figure out which base units were used to define the watt. And again, I'm not going to have you memorize this. I'll give you a copy of this chart. I'm just going to ask you questions like that. Figure out what do you have to do. It says a joule per second. Well, I got seconds. Now I got to find out what a joule is. I will say that a lot of these SI units are really creeping into our society, whether you think it's creepy or not. They are creeping in because if you were to buy something for your computers and you said, I want to make sure that if I have a lightning strike or something, it doesn't fry my computers, wouldn't you have like a, what do you call those, ground fault interrupters? You'd have some kind of a system that would prevent it. It would actually fry the system. Before it fries your computers, it fry the little plug-in thing, right? And if you buy one of those, I can't remember the name of them, it's actually rated for so many joules. And so you're going to see the word joule is going to come in. It's actually coming into your world. So joules are any kind of energy, electrical energy, heat energy, and you'll find that out that joules are coming into play. Of course, we've had meters and stuff like that. That's coming in. What do you think? Any questions about that? What'd you get? Ella, what'd you get? Tell me which ones.
Second meter and kilogram.
Say it again.
Second meter and kilogram.
Okay, so just 3 of them. Okay, let's take a look. The second for sure, and a Newton meter for sure. Then I have a kilogram. That's 3. Yes, that's very good. Any questions? So at least you understand that the SI system is kind of like they still have that connection. You know that? They want all the units to be connected somehow. And if we have time tomorrow, we may not, but if we have time, I'll show you the last video. They just made it because they just announced that they were going to change these slightly. They're going to change the definitions slightly, okay? All right, the last thing I'd like to do is, let's go to this page here. Oh, wait, I know where it's at. It's on the other packet. Oh, yeah, let's go through this right here. This is a little bit about the history, and we can actually add another one now, 2019 now, but I think the dates I'd like you to know here, and that's from the reading you had, is somewhere around 1795 is, even though they spent about 5 years developing this, the metric system started about right before 1800, okay? That's easy to remember. The next thing, what I think is kind of shocking, that the United States passed a law in 1866 that they said you can use metric units in the United States. Yeah, right. But they passed a law that said you could. So I guess that's all right. But this is the next date I thought was interesting. It's like, hey, this thing's catching on. It's catching on, and it makes sense. And somebody said, we should do this. And so there are about 17. This says 19. I read another book just recently, an article that says 17. So whatever. It's somewhere around 17, 18, or 19 countries. They all went to this meeting. And they said, we're in. We're buying into this metric system. Count us in. So a lot of your major countries, Spain, France, England, United States, we were in, and we said, count us in. We're going to go metric. And if you did, it took a little while, but then they built you your own little set of standards. And so we had, from the international prototype, they gave us a copy, which would be our national prototype. And so we have we had a piece of platinum iridium, which doesn't rust hardly at all, and it had 2 marks on it, and that was exactly a meter. So they got rid of the definition 1/10,000,000th of the distance from the North Pole to the equator. Get that? It became an actual piece of metal with 2 scratches on it. And then we also got a kilogram. We got our little copy of the kilogram, and so we were off and running. We should have been ready to go. What I think happened there is we were still trading very heavily with England with Canada with Australia, and we didn't have a really big need for other countries in Europe. We didn't really have to trade with them. And so we kind of resisted. England resisted, Canada. And really, England wasn't until 1965. They waited until 1965 to tell their country, all right, that's enough. We're trading a lot more with Europe, and we just got to go that metric thing. And so, anyway, this was interesting that we actually, we said we're in. They gave us some, our own standards. Here we go. All right, 1916. All right, let's form a committee and said, we're going to switch. We're going to do it. We're going to do it. What do you think? Did that happen? No, it didn't happen. Okay. 1960, somewhere around 60 to 64, they started making SI. SI was kind of a modernized version of the metric system, and they started redefining things. And instead of the meter being 2 scratches on the piece of metal, it became so many wavelengths of a certain kind of a light, and that's the meter was redefined to make it so you could measure even tinier things. Do you know that today's meter is actually based on the speed of light? So we redefined it again, didn't they? Anyway, and here's kind of a lame duck thing. Look at this thing. The Educational Amendment of 1974. What's that word? encouraged the teaching of metric system in the school. Okay, all right, good. Look at this one. 1975, encouraged the use of the metric system. But guess what? Did they say, like England said, you got 5 years, everybody? You got 5 years, and you can't use the pound anymore. You can't use the slugs or the poundals or anymore. You can't use it anymore. But we didn't do that. We didn't set a date. So guess what happened? Nothing. Okay? And then you have this right here. This is the only thing we actually did. But you know what? It's not like, oh, I love the metric system. No, it's people said, people made things. And he said, you want to sell these around the world? Well, if you don't have a metric unit, they won't even let you sell it. And you make what, pork and beans, and you want to sell it in Italy? You can't sell it in Italy unless it tells you how many grams it is. Okay, twist my arm. I'll put both labels on there. It wasn't because they were nice. They said, we might make more money. And so in our country, if you can tell somebody it might make you money, they'll do it. That's kind of weird. So anyway, that's kind of a quick timeline here of the metric system. Now, the last thing I want to do is, I think, here it is. Here's the page I'm going to look at. Today and half of tomorrow, all I want you to do is to concentrate on, do I know metric units? Can I estimate a metric unit? Okay? All right, let's try that. We did this in 10th grade. It should be easy. It should be better now. Paperclip. Why is there a picture of a paperclip on this page? And not a jumbo paperclip, just a regular paperclip. Okay? And I didn't have a picture of a nickel. I'm going to draw one. Yeah, a nickel really looks like that. Okay, but the reason I want to put a nickel on there is just a coincidence. It's a coincidence, but the one U.S. coin that is pretty close to a metric unit is a nickel's about 5 grams. Got that? That's pretty good. So how much would a quarter weigh? Oh, you mathematical-minded people. Okay. Actually, a quarter is a little over 5 grams. I know you thought it was going to be 25. No. Wait a minute. So this is the only one that's kind of close to a metric unit. Okay. A dollar bill is pretty close to a gram. Okay. Why is there a doorknob? Why is there a doorknob? What is it? Okay, so how tall is the ceiling in meters?
2.5.
Okay, how far is it across this room in meters? Ceiling. Let's do the ceiling again. 1, 2, less than 3, but maybe more than 2.5, maybe something like that. How about the doorway? How tall is the doorway? Okay. If I told you there was a person, a college, an NBA basketball player, would their head hit the top of that doorway?
Yeah.
Maybe. So how tall are they? What do you think? They're a couple meters. Are you a couple meters tall? I don't think so. How tall are you?
Mason's almost 2 meters.
Oh, how tall are you?
6'4", 6'5".
How many centimeters? Do you remember doing that thing the other day? How many? Are you like 180?
Yeah.
Something like that? Okay. All right. All right, let's go on. How about, why is there a picture of a dime here? And we had this before. We're just going to quickly review it. It's about a millimeter, right? 1/10 of a centimeter. It's about a millimeter. Everybody should be able to, everybody should be able to find with their little finger where a centimeter is. Now, my finger is a little bigger than some of yours. Some of yours, you go all the way down to the base of your little finger, and that's a centimeter. And some of you, it's way up here, like for me. This is not a great ruler, but I'd have to go like way up here. So my centimeter is way up there. And so if you have a chance to get a ruler, find out which part of your little finger is a centimeter. So you should be able to estimate centimeters. I don't really use the fingernail. Some people do. All right, which one's longer, a meter stick or a yardstick? Okay. So a meter stick is about 30 39.37 inches. It's a little over 3 inches bigger than a yardstick, right? Everybody got that? All right, that's pretty easy. Let's see, what else? Which one's bigger, a mile or a kilometer? Okay, and it says here a mile is about 1.61 kilometers, or a kilometer is about 0.6 of a mile. So if I were to draw a mile, half, a little more than half, I could draw a kilometer. So we estimate that? Okay. Let's go over here. You don't do real estate around the world, but you probably, if you read any kind of articles about the Amazon, I saw an article last week about island. Have you heard of Borneo? You ever heard of that island? And unfortunately, it's a great jungle-like island, and you have all these really neat animals there. But at least part of the island, they're starting to commercialize it or industrial. They're actually cutting down forests and stuff, which is a shame. But whenever you read that, you hear about, well, how much area is there? Look down here, and this is what they use around the world. I think maybe Scotland might still use acres, but I'm not sure anybody else uses acres except for us. Do you even know what an acre is? If I say go out and mark an acre off, could you do that? Could you put an acre on a soccer field? Yes. Most of you, if you live in a house and you're a little bit close to your neighbor, you feel like, well, we're not that far away from my neighbor. His house is right there, right next to him. If you're kind of squeezed in a little bit, your house is probably on 1/3 of an acre. If you have plenty of room and people come to your house and, hey, let's play baseball, chances are you might even have a whole acre. You got that? But that's a pretty big yard. If you have an acre yard, you could have kids come over, play a little baseball game, okay? A lot of people, if you can estimate acres, that's nice. But here's what they use around the world. They use a thing called a hectare. And what's a hectare? And I like hectare because it's a square. A hectare is a square. And how long is each side of the square? And this is what I like about it. What are the length and the width of this square? It's a hectometer. Ooh, I get it. A hectometer is 100 meter sticks. Take 100 meter sticks that way and 100 meter sticks that way. I can envision that. That's a hectare. All right. Who has their phone out? Who has their phone ready? You want to look something up for me? Look up how many acres. Who has a phone? All right. Look up how many acres is a hectare. Now, the rest of the world doesn't care about an acre, but I thought you might want to be interested in that. Do you have your phone with you?
I do.
Okay.
Oh wait, 1 hectare is 100 acres.
No, I don't think so. Now, 1 hectare is not 100 acres.
That's what my agenda says.
What? It says a hectare is 100 acres?
Yes.
No way.
That's cap.
Here, ask Siri. Say, Siri, how many acres are in a hectare? Well, just...
Sorry, I had to wait for it.
Let's go fast. Hey, Siri, how many acres are in a hectare?
2.47 acres.
Well, anyway, it's about 2.5. So if I took 100 meter sticks that way and 100 meter sticks that way, that would be a hectare, and a hectare is about 2.5 acres. Okay, everybody got that? All right, which one's bigger, a liter or a quart? A liter or a quart? Which one? If you take a look, the liter is being poured into a quart and it's overflowing a little bit, isn't it? So a liter is very, very similar to a quart. A liter is about 1.06 quarts, right? Everybody got that? So, how many liters are in a gallon of milk? That's a fair question. You live in the United States. How many quarts are in a gallon? There's 4. So how many liters are in a gallon? A little bit less than 4. Isn't that right? So a gallon is about, a little bit short of 4 liters. Is that right? I remember the first time many years ago, took a trip down to Texas. My mom had lived there, and we were down there, and I pulled into this gas station. I couldn't believe the prices. It was the lowest gas I'd ever seen in my life. I pulled in. I said, I'm getting a fill-up. And then, guess what it was? It was price per liter. No wonder it was so cheap. Because it's almost like I had to multiply that almost by 4 to figure out how much it was per gallon. Got that? Okay. Okay, and then we actually spent some time with the liter box. Remember that? Everybody got that? So we spent some time with the liter box, and I'm not going to do that again, but you should know the liter box really well before you take the test on Wednesday. All right, questions? I have one more thing for you to do, and we're going to run out of time today. I think it was the very front. Tomorrow, it's your homework. I'm not going to grade this, okay? We may do this tomorrow at the beginning of class, but I want you to be able to estimate, and you might say to yourself, it's not fair. People in Italy, they don't have to estimate feet and miles. That's too bad. Hey, too bad. You live in this world where you have to know both. You have to know both. There's no way somebody your age can go away and say, I'm not learning anything about metrics the rest of my life. It's very rare. That's going to be very rare for you. Okay, let's try number 1. Ready? Let's take I don't have the phone set up for that. That'd be neat to do a poll on this one. A gram is about the mass of what? What do you think? Oh, that's weird. That's weird. Okay, so anyway, tomorrow what we're going to do is we're doing a little bit of review tomorrow. I'll show you a short video that the updated version of the SI system, and I think that's going to about wrap everything up. We also I think we're going to have time to grade those homework you did. Might be able to do that. I kind of put that off. You guys all right? Monday morning, is that your favorite time, Monday morning?
Oh, yeah.
Okay, thank you. That's what I thought. All right, well, thank you very much. And wait, I'm early, aren't I? Sorry, never mind. Let's do this for a little bit because I'm too early. All right, a gram is about the mass of what?
Take the clip.
Okay, that was an easy one. Next one, number 2. What do you think? Okay. Number 3. Okay, everybody got that one? Okay, number 4. I think the girls are going to be better. I'm not trying to be sexist. The girls are going to be better in this. Sometimes you ask the guys, how much do you think a newborn baby? I don't know, 20 pounds? And the girls go, oh, right? There's a lot of guys have no idea. They have no idea about babies. Anybody have an idea? What do you think? C? Okay, girls, what do you think? A kilogram is about 2.2 pounds. 3 kilograms would be about 6.6. Oh, it's very good. Very good.
I was a lot heavier than that.
You could have been, but you weren't 20 pounds. No. Okay. Next. Kilo. Anyway, what I'd like you to do here for the next 4 minutes or so, go through here and see how many of these you absolutely say, I know those. And then the ones you're not sure about, put a little question mark on, okay?
That's homework.
What now?
Is that our homework?
That's not for a grade. I'm just going to do that for the next 3 minutes till it's time to leave. So just go ahead and go through there and see how many of these you can do right. I'll give you the answers when I get done.